Today, we're going on a journey deep, deep inside the human brain to explore its most complex, most hidden network, the white matter. And you know what's really cool? We're going to see how a technique that's almost 100 years old is still one of the best tools we have to understand it all. So, you ready to map the mind? Let's dive in.
You know, when we picture the brain, we almost always think of that wrinkly gray surface, right? But that's kind of like just looking at the cover of a book. What's really going on underneath all those folds? What's connecting everything? Well, that's what we're about to find out.
So, this is it, the cerebral cortex, the famous gray matter. This is the brain's command center. It's where our thoughts, our memories, our biggest ideas, it all happens right here. But for any of that to actually work, information has to travel, and for that, we've got to go deeper.
And what's down there? It's just this incredible, complex web of nerve fibers. Think of it like a biological internet, with information zipping around at, get this, up to 268 miles per hour. This is the white matter, and figuring out how to map it has been one of the biggest challenges in all of science.
Okay, so before we get into the how, let's just make sure we're all on the same page about the two main players here, the gray matter and the white matter. The easiest way to think about it, it's the difference between the computers and the cables.
It's a really simple but super helpful way to look at it. The gray matter, that's all your computers. They're the processors doing all the heavy lifting, all the thinking and feeling. And the white matter, well, that's all the cables. It's this massive, sprawling network of fibers that connects all those computers and lets them talk to each other. One processes, the other transmits. You absolutely need both to have a working system.
So, how in the world do you map something that's so incredibly delicate and tangled up? For centuries, scientists tried to untangle these cables without just destroying them. And then, along came a neuroanatomist named Joseph Klingler, who, way back in 1935, had a revolutionary idea.
Now, people had been trying to do this for a long time. Since the 1800s, pioneers were making these amazing first attempts. But it was Klingler's work in the 30s that was a total game changer. And it all led up to his incredible atlas in 1956. He literally found a way to make the invisible visible. And this slide just shows you that jump perfectly. On the left, you've got this 19th century engraving. It's remarkable for its time, but it's flat. Then look at the right. That's a brain prepped with Klingler's method. The detail, the way you can see the fibers in 3D, it's just on another level. So, what was his big secret? The secret, believe it or not, was freezing. Klingler figured out that if you take a brain that's been preserved and you freeze it solid, tiny ice crystals form in between all those nerve fibers. And then, when you let it thaw, the ice melts and leaves these perfect little gaps, gently separating the fiber bundles. They're basically ready to be peeled apart, layer by layer. It's such a simple idea, but absolutely brilliant.
Okay, so we've covered the what. Now let's talk about the how. Because this isn't some quick and easy procedure. It's more like a meticulous art form. It takes an incredible amount of care, patience, and serious expertise.
So, the whole thing starts by preserving the brain for at least 2 months. 2 months! Then, it gets frozen solid for 10 days. After a really slow 24-hour thaw, the real work begins. A very delicate, layer-by-layer dissection using, often just simple wooden tools.
And here, we can actually see that process starting. It's like peeling an onion, really. The dissector is carefully pulling back the outer layers of white matter to get to what's underneath. You can see the lentiform nucleus there, marked as number 1, and those fan-like fibers of the corona radiata, number 4, just starting to peek out.
And as we go deeper, the major pathways just pop. They become so clear. Here, that lentiform nucleus is gone, and bam, there's the internal capsule, number 1. This thing is a massive information superhighway. You can follow it right down as it funnels into the brainstem at number 3. It's incredible to see it laid out like that.
So what does it take to do this work? Well, it's not a bunch of high-tech gadgets. It's an encyclopedic knowledge of the brain, a surgeon's steady hand, and just a ton of patience. The main tools? Simple wooden spatulas. It's all about the skill of the person doing the dissection.
All right, so now that we get the how, let's get to the payoff. What does this technique actually show us? What amazing architecture does it reveal about the brain's internal wiring?
And this is the payoff. Just look at that. It's a breathtaking view of the brain's white matter. You can see those corona radiata fibers, number 5, fanning out like a firework explosion, and they're all funneling down into that central highway, the internal capsule.
This is the physical network that controls our movements and processes what we feel.
And it's so important to remember, these are not just random wires. They are organized into very specific circuits. A lot of these bundles make up what's called the limbic system. That's the wiring that governs our memories, our emotions, our behaviors. It's literally the architecture of who we are as people.
What's really cool is that Klingler's method helped us see a beautiful, simple pattern in all this complexity. The main highways of that limbic system are actually arranged in two big rings, one inside the other, all circling around the brain's central relay station, the thalamus. An inner ring and an outer ring, each with its own job to do.
And this view from the side just shows it perfectly. We're looking at key parts of the memory circuit here. See that big C-shaped bundle at number 13? That's the cingulum, part of that outer ring. And right inside it, in number 5, is the fornix, a key part of the inner ring. And look, they're both wrapping right around the thalamus, number 8. It's just elegant.
Okay, so let's be real. This is a 90-year-old technique. It takes a ton of time, it takes a ton of skill. In an age of MRI machines and super advanced brain scanning, why is this still so important? What can this old method teach us that a new scanner can't?
Well, the answer is pretty simple. It provides the ground truth. As this quote says, for a neurosurgeon who's about to operate on a brain tumor, or for a scientist trying to understand a disease, you need to know the actual physical layout of these pathways. This isn't a simulation, it's the real thing. It's the difference between looking at a map and actually standing in the city.
And this isn't a case of old versus new. It's really about teamwork. Modern MRI techniques let us see these pathways in living patients, which is obviously critical for planning a surgery. But the Klingler method, that's the gold standard anatomical map that lets us double-check and correctly understand what we're seeing on those scans. It's how we know we're reading the map right.
So here's the bottom line. The old informs the new. This incredibly painstaking, hands-on technique gives us the fundamental 3D knowledge we need to make sense of our most advanced technology. It's just a beautiful testament to the power of seeing things with your own two eyes.
And it just leaves you wondering, doesn't it? With all these incredible tools, both old and new, what other secrets are still tangled up inside the most complex structure in the known universe? What's the next generation of explorers going to find when they set out to map the mind?